Hello everyone, my name is Tongjie Wang. As a ESE-5130 Quantum Technologies video project, today I'm going to introduce Superconducting Nanowire Single Photon Detector, or aka SNSPD. So I'm going to firstly talk about the motivation and potential broad impacts of this technology. It was first designed to detect photon and corresponding energy, and it was widely used in area of quantum information, especially in quantum key distribution and optical quantum computing. Here are the just two pictures of corresponding area. It has been incorporated into many other different fields, such as imaging of infrared photon emission for defect analysis in the CMOS circuitry, which is just the picture on the bottom left. And other fields such as on-chip quantum optics, readout for ion trap qubits, single electron detection, deep space optical communication, which is the image showing on the bottom right, and also dark matter searches. So before we proceed to the next topic, I want to introduce two key concepts relevant to the photon detectors. First one is quantum efficiency. This indicates the probability that the detector successfully generate electrical signal when it receives a photon. So this is usually expressed as a percentage. High quantum efficiency means that the detector is able to convert incident photons into signals at a higher proportion. And this reflects the photon's detection ability of the detector, and it is an important parameter to evaluate the sensitivity of the detector. The second one is dark count rate. This dark count rate refers to the frequency at which the detector generates an error signal without receiving a photon. So ideally, a photon detector shouldn't produce any signal when there's no light incident onto it. But in practice, the detector may still produce counts due to thermal noise or other kind of electronic noises. So the lower the dark count rate, the higher the sensitivity of the detector. And this is very crucial to reduce the noise and improve the reliability of the detector signal. Lower dark count rates are especially critical for detecting weak signals, such as single photon. Here are some examples of competing technology, and I'm going to introduce briefly about their advantages and disadvantages. The first one is called avalanche photodiode, aka APD. This one is a single photon detector based on semiconductor material that can operate over a wide range. And its advantage is it is pretty low cost, small size, and it can operate on relatively high operating temperature. But the disadvantage of this is the dark count rate is pretty high, and the quantum efficiency is not as good as SNSPD. The second one is called photomultiplier tube. This is a conventional photon detector that is widely used to detect single photon in the ultraviolet to visible wavelengths. The advantage of it is it can respond pretty fast and suitable for low light environment. Disadvantages are it has low quantum efficiency and detection rate, especially in the infrared region. And the dark count rate is pretty high. The third one is called quantum dot photo detector. This is a new single photon detection technology. It has high quantum efficiency in some cases. So the advantage of this device is it can adjust its wavelengths and it has relatively high quantum efficiency. But the disadvantage of this is that detection speed and dark count rate is not as good as SNSPD because this one is, as I said, just some new technology. So comparing to competing technology, the advantage of the SNSPD is that first, it has high quantum efficiency, especially in the visible to near infrared spectral range. And second, it has very low dark count rate, making it very sensitive in detecting single photon. And third, it has very fast response time. And lastly, it has a relatively wide spectral response. The disadvantage of it compared to other competing technology is that it requires extremely low temperature, around 4 Kelvin, and secondly, it has relatively large size, and lastly, it has high cost. The SNSPD was first developed by scientists at Moscow State Pedagogical University and at the University of Rochester in 2001. The first fully operational prototype was demonstrated in 2005 by the National Institute of Standard and Technology. So here I will introduce briefly the principle of technology. The first part is superconductivity. So we know in a conductor, all those electron carrier charges are moving freely, and some of them, when they move, they may sink into the lattice structure. This is the source of the resistance. At near absolute zero temperature, however, those electrons, they may form a pair called Cooper pair, and those Cooper pairs allow them to move freely without sinking into the hole between the lattice, and that's why we have a superconductor. So as for the SNSPD, first we have a bunch of superconducting nanowires. Then at stage 2, a photon is incident onto the nanowire, causing a hot spot. This will cause current density around the hot spot to exceed critical current density that a nanowire can carry, and the surrounding superconducting state is destroyed as well, which is stage 3. We can see the hot spot is actually growing larger. As this continues, we can see a blocked region across the entire nanowire, which is stage 4 and 5. And finally, under the interaction of dynamic change of current and electrothermodynamic feedback of Joule heat relaxation through the substrate, the inhabited region first grow and then decrease, which is the stage 5 and 6. The result of this is a voltage pulse that we can measure. And that's basically how it works. Okay, finally, let's talk about the SNSPD state of the art and also challenges. First of all, the SNSPD have very high quantum efficiency, over 90% in the near infrared region, and which are considered one of the most efficient single photon detectors. And second, it's extremely low dark count rates, down to only a few counts per second or even less. This is really advantageous when we are trying to detect weak signals. And thirdly, it's fast timing resolution on tens of picoseconds. This feature is crucial for applications requiring high time resolution, such as time-correlated single photon counting and certain type of imaging. And lastly, it has a relatively broad spectral range, which is range from visible to middle infrared. And lastly, some of the challenges of the SNSPD. First of all, its cryogenic cooling requirement. SNSPD must be operated at very low temperature, typically below 4K Kelvin, to maintain its superconductivity. This requires a costly and complex cryogenic cooling system, which often uses liquid helium or closed-cycle cryocoolers. And secondly is quantum efficiency. Even though SNSPD exhibit high quantum efficiency in the near-infrared region, their efficiency decrease outside this region, especially in the visible and mid-infrared regions. And thirdly, it's operating wavelengths, so it cannot be used for far infrared regions. And lastly, on-chip integration. For application in quantum computing and photonic circuits, it is essential to integrate SNSPDs directly onto chip alongside other photonic components. However, because of the cryogenic requirement and the physical complexities, this is still a pretty much challenge today. Okay, that's all I got for the superconducting nanowire single photon detector. Thank you very much for your patience. And I have also included some of the key references here.